Now, as chemistry jokes go, I think you'll all agree this is the timeless sort of ultimate classic. There it is. Anyway, so this is a very short sort of look. There's not a huge amount to say here. Two more sort of chunks of the periodic table. First of all, the noble gases, which we're going to call Group Zero, but which are also called Group 8 and sometimes Group 18. And then also, not really a group per se, but a large chunk of the periodic table, which are the transition metals. And we're interested in how they compare with, for example, the group 1 metals. What are the similarities and differences? So hopefully you can see the joke here. Noble gas is already full. They've already got a full outer shell of electrons. There's no reason why a noble gas would react. Well, there are actually, but then beyond GCSE yet again. But in terms of getting a full outer shell, there's no driving force there because they've already got one. So unlike Group 1 and Group 7, they don't react to get a full outer shell. They don't need to achieve that. They've already got it. So what do we know about the noble gases? Well, there's a video for you to watch. It's only short. See how much use you find it. Go and watch that first. It's linked in the classroom. Watch it, see what you think, and then maybe come back here at that point and take these notes. That's all I've got to say about that. So carrying on now, assuming that you've watched the video, hopefully you found it interesting. What is there to say? So as I've already mentioned, Group 8 is another term that's sometimes used for the noble gases. That thing about number of group number equal number of outer shell electrons doesn't really hold for the noble gases. The one thing we can say is, as we already mentioned, and as that cartoon tried to get us to appreciate, they already have a full outer shell. Helium's only got 2 electrons in its outer shell, and that's full. The others mostly have 8, or they actually all do have 8 electrons to have a full outer shell. So group 0, the 0 doesn't mean number of electrons in the outer shell, nor would the number 8 because helium. But it wouldn't be right to call it group 2 because that doesn't make much sense either. Anyway, so be aware of that. They are very stable elements, meaning they don't react readily because there's no driving force basically. There's no need to get a full outer shell that hasn't yet already been fulfilled. And so, as we've said, that means that's really where the name noble comes from, the idea that they don't attack things, i.e. they don't react with them. That isn't completely true, you know. Helium, neon, and argon, the first three noble gases, are extremely unreactive. There are some sort of debatable compounds of one or two of those elements, but they're very exotic. They're not like conventional compounds. They've got weird bonding, in other words. But krypton and xenon, lower down group 0, they actually do form compounds quite easily, especially with very reactive substances such as fluorine. That's not for us to look at right now, but just be aware that the noble gases aren't completely unreactive. They're just very, very unreactive compared to the other elements. Now, another interesting thing, in that video, if you watched it, hopefully you did, you'll have seen density. The xenon balloon drops like a lead balloon, but more like a xenon balloon, I suppose, whereas the helium one floated and the others in between. Density varies because we say that all gases are roughly equivalent. So this graph here is boiling point, as you can see from the x-axis. But let's just talk about density a little bit more. 1 mole of a gas occupies 24 dms cubed of volume. That's something we caught from our moles topic back in year 10. 1 mole of a gas occupies 24 litres at room temperature and pressure, whatever that's supposed to mean. So 1 mole of xenon weighs a lot more than 1 mole of helium. So 24 litres of helium, a mole, weighs 4 grams. 24 litres of xenon weighs, well, it's MR in grams, or rather it's formula mass in grams, which is much heavier than 4. So that's how density sort of works. You can see that all gases are equivalent in amount of substance per unit of volume, but the mass can vary of those number of particles. Here we're looking at boiling point. It's the same trend in the increasing mass of the particles. These are single atom particles. There's no need for them to form diatomics like Cl2 does, or metallic lattices like silver and cesium and sodium and so forth. But yeah, as the particles get bigger and also along with that more massive, they have higher boiling points. That's because the electrostatic, sorry, try again. I'm going to take that back. That's because I'm going to call them intermolecular forces between these noble gas atoms that get stronger. Just like the reason why a big hydrocarbon has got a higher boiling point than a small hydrocarbon, it's because there are more intermolecular forces between the bigger particles. Even though these aren't molecules, they're atoms, they're single atoms, they're not multiple atoms, so they're not molecules. Xenon's just bigger than helium, a lot bigger, and so it's got stronger intermolecular forces, it's got a higher boiling point. Anyway, there you go, fun fact for you. Hopefully that makes sense. Onto the transition metals then. Now, again, I can't help myself. I need to put a bit of a disclaimer on this. For GCSE, it's perfectly fine to say that all those elements coloured in green are transition metals. That's not quite true. We're not going to talk about why, but actually titanium to copper, they are, the columns below, but the column headed 3B and the column headed 2B, not actually. But I'll tell you all about that in year 13 if you're still with us then doing chemistry. So the transition elements in general are that bit in the middle, that bit that's shaded in, as I trust you already knew. Look at the elements there. There's a lot that you won't be very familiar with, but that's where some of the most famous elements are. Silver, iron, gold, copper, chromium, all sorts there. They're also some of the most useful metals. Sodium's not very useful. Sodium's, as you know, it's in group 1. Cesium, interesting element in group 1, not very useful. It's too reactive. These elements are less reactive, and they tend to have certain physical properties that mean they're just more useful to people as metals. So how many wires have you ever seen made out of potassium? The answer is none. How many have you seen made out of copper? Well, pretty well all of the ones you've ever handled, all the wires. Okay, so there's something in that. Anyway, so they are quite a varied bunch. They're all metals, evidently, but they are a pretty varied bunch actually. There's quite a lot of diversity in the transition metal elements in terms of their physical properties. And within that, I'm talking about conductivity, melting points, boiling points, hardness. Lots of variety to be found when you go digging around the transition metals. And there are just some of the most important elements. Some of them you'll know much better than others. So what can we say about them? Let's make some more notes on this. It's a bit of an info dump here, I'm afraid, folks, but it's hopefully quite interesting and hopefully quite straightforward. Unlike Group 1, we'll see if you can beat me to this. Pause if you want. How would you say they're different? If you need more time, then do pause. If you're ready to just carry on, then keep listening. Well, they have higher melting points. Transition metals tend to melt at much higher temperatures than the Group 1 elements. When you drop a bit of sodium or lithium or potassium into water, as we saw last lesson hopefully, it fizzes, it moves around, so it's less dense. Here we're talking about melting point, and it melts. If you throw a bit of sodium onto water, it turns into a sphere of molten sodium. It's not like glowing hot, but it's molten, and it melts at a low temperature, relatively speaking. Copper and the others don't. There is one exception to that though. Which transition element has an unusually low melting point? Answer: mercury, to liquid at room temperature, so that's got an even lower melting point. It's a diverse bunch, there's a lot of variety in that, but generally speaking, the transition metals have much higher melting points than Group 1, on average, for sure. They're stronger and they're harder, so they're less difficult, they're more difficult to break, and they're more sort of hard wearing, basically. They won't break apart very easily, and they'll break other substances. They're less reactive. We know that copper will oxidize, it'll go a sort of green colour, of what's called verdigris, if you leave it out for a while. We know that iron rusts. We know that basically all metals will oxidize, maybe apart from gold, platinum, silver, and some of the really, really least reactive elements. But generally speaking, they will react, but much more slowly. Compare the speed of rusting with the speed of potassium reacting with oxygen. There's a huge difference. The Group 1 metals are much quicker to react with oxygen and water than the transition metals will. They have variable oxidation states, or as we tend to say at GCSE level, variable charges. So whereas there's only one charge possible for a Group 1 metal, and it's a 1+ ion when it's reacted into a compound, iron can form iron 2 and iron 3. Manganese forms Mn2+. Now look at that. I've purposefully used a Roman numeral there. I've said manganese 7. That's basically saying Mn7+, but it's not actually 7+. And again, there's clearly a bit more that I'm not telling you there. Fine for now. Learn about it in the future if you're still doing A-level in next year or two. So yeah, they can have variable charges. They're not fixed. Copper, most famously, is copper 2+. However, there is also copper 1+. It's pretty rare, but it happens. Interesting fact for you. I'm not going to put this into your notes. I'll just tell you for those who are really listening. Zinc. Zinc's not a transition metal. We say it is at GCSE. It's in that block that was coloured in green at the start of this section, but it's actually not a transition metal. It only has one possible charge. It only makes zinc 2+. Why is that? Well, lots of reasons, okay? But the ones that are truly transition metals have got multiple charges, and that's pretty well all of that block that I showed you at the start, coloured in green. What else about transition elements? Well, generally speaking, they form coloured compounds, whereas the Group 1 metals don't. Now, I've got to be careful here, because there's lots of colourful chemicals out there that are absolutely nothing at all to do with transition metals. However, if you have got a transition metal compound, then it will be colourful. And if you've got a compound of a metal which is not a transition metal, the chances are that metal compound won't be colourful. So I could predict quite confidently that rubidium chloride, rubidium's in group 1, RbCl, rubidium chloride, without ever having seen it in my life, I guarantee you it's a white solid and it's a colourless solution when it's dissolved because it's not a transition metal. Whereas iron chloride, well, it depends if it's iron 2 plus or iron 3 plus chloride, if it's FeCl2 or if it's FeCl3, that will have a colour other than colourless. You get the idea? And it does actually, it's yellow. They're both yellow actually. Anyway, there you go. So those are the really key properties. One more thing to say, interestingly, though again it's beyond GCSE where we actually look at how that works. But the fact that these ions, these transition metals can form different charged ions, like iron 2 and iron 3, that actually has quite an important knock-on effect. That makes them very useful catalysts. There's more to it than that, evidently, but just be aware for now that some of our most famous and most useful catalysts in industrial processes are transition metal based. You've met iron, Fe, as the catalyst in the Haber process for making ammonia from nitrogen and hydrogen. There are lots of catalysts that aren't transition metals, I've got to say that again, but many transition metal compounds and transition metals themselves are good catalysts for something, and it's because of their interesting electronic structure. It's to do with the fact that they can form multiply charged ions, like it could be this or that or the other. So I did say it'd be short, and that is all there is to say. Once again, for this topic, I'm flashing up what the spec has to say. Double check it. We've given a whistle-stop tour here. You can see if you look at the transition metals, they specify these 6 elements. Now, that doesn't mean that you're supposed to go and memorize the melting points, the conductivities, the hardnesses, and so forth of those 6 elements. But what it might mean is that the examiner gives you examples that relate to those elements and ask you to talk about it. So, for example, and they might want to catch you out, get this one, they might ask you to compare manganese with magnesium. Not very friendly if you're dyslexic, because they're pretty similar words, but it'll catch a lot of people out regardless. Manganese, Mn, is a transition metal. Magnesium, Mg, well, okay, it's not in group 1, it's in group 2, but it's similar and it's not a transition metal. So magnesium sulfate would be a white solid, manganese sulfate will be colourful. Okay, we'd have to be told what colour, and so on. So those are the sort of things you could be talking about. Okay, now other than that, that's all there is to say. That also brings to a conclusion this relatively short periodic table topic that started with the history of the atomic structure model. There's more to do. There are some questions to answer on this periodic table topic for my class now, so go and have a look at those.